Let's test if this mic works. Seems to work. So let's edit. I forgot to edit the title. Physics. What else? What? I can't scroll. Public. What is going on? I need to save, my guy. Save. Changes saved. Yes. It works. So yes, I've got my setup. I've got the stopwatch ready. I think it works. Yeah, right. Yep. Let me see the connection here. So today we will be doing some physics. Physics HL 2024. See, I've got the chat here as well. I hope this whole chat is not available. What do you mean? What do you mean? Oh yes, got it. Yep. Welcome back, guys. We're back with physics. Physics, yeah. So what should we do? Mechanics, thermal physics, oscillation and waves, electricity and magnetism. Also, is my mic okay? Sand Monster 95, is my mic okay? I put it a bit louder. Yes, my mic is good. So what should we do? This I actually maybe need to revise because it's a lot of revision stuff. Circular motion, yeah, I also need to revise circular motion. Where's circular motion? And gravitation. Yeah, I'll do circular motion. There's only 2 topics, so hopefully it's not too long this time. Let's see, how many questions? Oh no. Oh no. Also, my camera's in front of the chat. Let me move it to that side. It's probably better. I need to remember. Can you see the chat now? Yoo-hoo. So, how many? There's a lot of multiple choice though. Ah, I spoke too fast. Okay, there's a bit more questions. There's 60. So, let's speedrun this. Oh, no, 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 stop. No, my setup. I just messed up my setup. Forget about it. Okay, we're back. So, question 1. Let's see what this topic is all about. Which of the following is correct about gravitational fields strength at a point near a planet? Is the force of gravity acting on the object? Is the force per unit mass acting on a point mass at that point? Distance of the center at that point is independent of the mass of the planet. So that's... Is it the force per unit mass? Yeah, I got 5 subs. I actually don't know. I'm gonna go with B. Okay, good start. An object of mass m on a string moves in a circle of radius r at constant speed. Which of the following statement is true about the motion of the object? The resultant work done on the object is 0. Wait, let me mute myself because I've been speaking in my ears all this time. Yeah, if you have any ideas, yeah, go ahead. Which of the following statement is true about the motion of the object? The resultant work done on the object is 0. Yeah, because there's no displacement. So I'm going to say true. The velocity of the work is constant. No, the velocity of the object is constant. Yeah, that's true. Oh, no, it's a change of velocity. It's wrong. The object is accelerating, that's true. Because the velocity is not constant, so these are exclusive, right? So we're gonna go with D. Let's see if you put D. D, yeah, correct. Next. An object moves in a circular path of radius 2m with an angular displacement of this rad in 5 seconds. What is the linear speed of the object? Let's check in the formula booklet quickly. Hope it brings me. Oh, it doesn't bring me. I'm gonna have to click on this every time. Oscillate. What are we doing? Circular motion. I should have probably a physical copy of this because it's gonna be really annoying, isn't it? We're looking for centripetal, so it's WR. So 2 times W, W. Yeah, I should get a real copy. I'm just gonna get a real copy, and you can think about this while I'm gone. We're back. So I got this colored copy. I hope my teacher forgives me because I'm not supposed to have this colored copy. So circular motion. Circular motion. What can we say about this? So W is equal to. There's no definition for W. Can someone explain why there's no definition for W? Isn't it in another topic? It's in the HL thing, isn't it? This is going great. I thought it was in the HL thing. Topic 9. Yeah, it's over time period. W is this, yeah, it's the velocity, but how do you get that W? How do you get the W? Uh, well, if it is it just 2 pi divided by 5? Pi over 10? Is this what it does in 1 second? V divided by R. Yeah, but we're looking for V. So I'm just gonna assume it's pi over 10, and then radius 2, so then it's just pi over 5. C. Is this correct? Okay. W's, yeah, okay. Angle divided by T. Question 4. The gravitational field strength on the surface of the moon is this: two objects of different masses, m and 2m, are released with zero speed on the moon. From heights h and 2h respectively, where h is small compared to the radius of the moon. What are the magnitudes of the acceleration of these objects right after release? The two objects of different masses, m and m2m, are released with zero speed on the moon from heights h and 2h, respectively, where h is small compared to the radius of the moon. Okay, so, okay. Released. The acceleration. Wait, doesn't it not matter if h is small? Right, because it's the acceleration right after. You can get permission to leave whenever. I don't mind. GE6. Mass M. Mass M. Release with zero speed. So if we assume h doesn't make a difference, then it's just this. And G is, doesn't matter unless divided by, it's force divided by mass. So if mass is 2, it's going to be divided by A. Let's go with A. It's B. So what are you on about? Continuous F equals MA. Okay. Weight equals mg. Weight equals mg6. A equals g over 6. It's not dependent on magnitude of mass and height. It is equal to the acceleration of free fall. Oh, it's not dependent on mass. Wait, what's F divided by m then? Right, of course it's not dependent on mass. But F divided by m. We off on a good start, aren't we? Right, let's see this quickly on the formula booklet and see if they define m. Yeah, okay, it's just mass. M is just mass. Okay. So, yeah. The following statements are given about the forces acting on a satellite in orbit on a planet. The gravitational force on the satellite is proportional to the mass of the planet, and the gravitational force on the satellite is proportional to the mass of the planet and the mass of the satellite. The strength of the gravitational field is equal to the weight of the satellite. I think mass shouldn't matter, or does it? It's like the type of thing, yeah. In orbit, is there another section to this? No, there isn't. I really don't remember this. Oh, I think it's this equation. Oh no, yeah. Oh yeah, that's centripetal force It's the mv squared divided by r. So let's say 2 is wrong and 1 is correct. So that leaves us with either this or this. Centripetal force acting on the satellites provided by the gravitational force between the planet and the satellite. Yeah, okay, let's go with C. C. Is the gravitational is not given by the force. It's correct because gravitational force is the only force acting on the satellite. Okay. Wait, did I start it? I didn't start it. I think what? How long has it been? Can you see? Like 15 minutes? 13 minutes? Can we add 13 minutes? No. Fair enough. Did I pause it? Spaceship A orbits Earth with an orbital speed VA and an orbital radius R. Orbits Earth with an orbit. Wait, is this HL? No, it's not. It's not. So I don't have to worry about the HL orbital things. Spaceship B orbits planet X that has a mass twice that of the Earth. What will be the orbital speed of Spaceship B if it were to have the same orbital radius as Spaceship A? Spaceship B orbits planet X. Okay, so we're looking for orbital speed. Orbital speed then is given by, is that just omega orbital speed? Or is it V? No, it's probably V. So omega R. But mass is changing. Orbital speed then is, okay, it's the mv squared divided by r. So if mass doubles, f doubles because it's proportional. So you got f times r. Oh, my face is covering the timer. What can I do? Add more tabs. You know what? Oh, my god. There we go. Add more tabs. Add more tabs. Is that fine? Problem solving 101. Can you see the timer? Yeah, probably. No, you can't see the timer. So where was I? F is doubled. R is the same because it has the same orbital radius. M is 2, and so it's going to be B because it's, wait, times. Oh, I forgot F was 2 as well. Let's just see. F divided by R. Huh? What are you talking about? G. Then V equals, yeah, 2M. So which mass is it using? Okay, it's replacing F on F, canceling the small mass, which makes sense. Oh, I guess you have to do that because it's big M. Therefore, F. Wait, what did we say about the mass of the planet? Okay, that makes sense. Again, we'll learn from that. Two objects A and B are separated by distance R. Let me start drawing things. Maybe I'll stop getting every second question wrong. A and B are separated by a distance R. The mass of A is much larger than that of B. The mass of A is much larger than that of B. Okay. Which of the following is correct about the magnitude and direction of the gravitational force exerted on A, exerted by A on B? Magnitude. What do you mean same? Oh, they have. Oh, compared to that, exerted B on A. Well, direction opposite. Magnitude same. Is it same? Because their mass is much larger. So. Well, no, but it's M and 1, so they need both. So you're right, it's B. Well done. Shout out to the Sound Monster for getting it right. Jet craft is performing a loop-de-loop, right? Stunt in which it is moved in a vertical circular path as shown. Which of the following represents the free body diagram of the pilot at the top of the loop? At the top of the loop. Yeah, it has a thing inwards. It needs to be balanced. Yeah, it needs to be balanced. No. Does it need to be balanced? It needs to be, I'm guessing, because he's not like, flying out, right? But he also needs to accelerate in the center, so maybe it's B, because he needs to accelerate in the center. Let's go with B. It's accelerating, right? So what is, what? Seriously? Yeah, normal force, true. But what? How does this even work? How does this even work? Why isn't he just like, there's no force, I guess there isn't a force. Well, isn't there a change of velocity? Well, every force is in equal and opposite reaction. So for there to be a normal force, there needs to be a force pushing it up. So why don't you write that? What? Not the chair as well. Yeah, there's a guy, but there to be a normal force, there needs to be a force pushing against it. Because that's what normal forces are. From the chair onto the person. This will act vertically downwards. And the weight is there, but I could watch the video, but you guys won't hear it because I turned it off. Wait, there's no video? There's no video, so it don't help. Why is this the only one without a video? Okay, I guess these are too easy. We shouldn't be getting these wrong. A stone. A stone attached to one end of rod. A stone attached to one end of a rod rotates in a vertical circle at a constant speed. Two positions of the stone at two different instants x and y are shown on the diagram. Below which row is correct for the centripetal force acting on the stone x and y? Magnitude of the centripetal force. Wait, is it vertical? It's vertical. So I'm guessing direction of the centripetal difference same? Is this C? Let's just go with C. I don't have the time. Okay. A satellite in a circular, oh, we did a sixth. A satellite in a circular orbit of radius r around a planet of mass m. Wait, a satellite in a circular orbit of radius r is in a circular orbit of radius r around a planet of mass m. Which of the following graphs represent the relationship between the centripetal acceleration of the satellite and its orbital radius. So as the orbital radius increases, it should be an inverse B. No, inverse is C. C. Yeah, okay, inverse. Wait, what? Why is it talking about this? Oh, did I just accidentally get it right? Centripetal acceleration of an orbiting satellite is the gravitational acceleration of the planet, which is given by this. Since the gravitational acceleration is inversely proportional to the square root of the orbital. What do you mean the delay is really bad? Oh, in the comments you can see the delay. True. Yeah, but it's always bad, isn't it? Well, my delay of the sound isn't bad. Yeah. Not this bad. Yeah, see, the delay's not too bad. Sorry. An astronaut in a space station brings the Earth. I can't read. An astronaut in a space station orbiting the Earth experiences weightlessness. Yeah, I got 10. See. The orb, yeah, experiences weightlessness. Following are three statements about the astronaut and the space station. The astronaut experiences no gravitational force. That thing that's wrong. That's wrong because it's just, yeah. The centrip. Wait, do we need the true? Which of these is correct? Okay. Centripetal acceleration of the space station is equivalent to the gravitational field strength at that location. Is it though? Is it though? Probably not. Both of the astronauts and the space station have the same acceleration. That's probably true. I'm gonna go with the 1 and 3. B. Okay, wait. The centripetal force is the gravitational force. Yeah. And oh, centripetal acceleration. Yeah, I was mixed up. Centripetal acceleration of the space station. Centripetal acceleration. What even is that's like the acceleration of the center? Which of the following graphs shows the variation of gravitational field strength of a planet with distance r from the surface of the planet? Gravitational field strength with distance r. Ow! It's r squared. Is it b again? Oh, but we have to make sure. Is this from the surface? So it's going to be b. Okay. Yeah, if this was from the center, it would be different. An airplane in straight level flight experiences a lift force L that is proportional to the speed of the plane and is perpendicular to the axis of the wings on the tail. On a banked turn at the same speed, the wings make a small angle to the horizontal. Which of these following gives the centripetal force on the airplane? Do you just resolve L, B? Or is it the weird tan thing that always comes up? Let's just go with B. Sine? What? Yeah, you make an... Oh, this is the angle. Okay, that's what you mean from the normal, not from the... I guess you need to read the question. Yeah, let's see. A geostationary satellites are satellites that complete one circular orbit in the same amount of time it takes for the Earth to rotate once on its axis. A geostationary satellite is placed in an orbit at this above the Earth's surface at the equator. The radius of the Earth is this. A satellite undergoes uniform circular motion. Define gravitational field strength. The forces experienced by a small test mass per unit mass, the average force per unit mass, due to a bigger mass. What are the experienced by a small point mass at a location? That was probably good enough. Show that the linear speed of the satellite is approximately this. Linear speed seems to be I thought geostationary satellites. Oh, because the Earth moves. Oh, that's how they work. Yeah, they just sink. I forgot somehow. It's placed in an orbit at this many, so we know the distance. They're trying to trick us with the Earth radius, but we know the distance to the center. We also know, yeah, its time period. So I guess we can use this time period. We can use v equals omega r. Omega squared r equals a, right? Yeah. So we are gonna use the time period, which in seconds is 360 times, wait, no, 365, 365 days, times, how many hours? 24? Times how many minutes? Times how many seconds? Is this correct? I think so. So we're gonna take that number, and we are gonna divide. So what is omega? It's the 2 pi, so 1 revolution. 2 times 3.1415, 926,535, whatever, divided by, paste. We've got an extra small number. That means times by the radius, and also on the radius, which includes the Earth orbit. So it's gonna be, I can't do that on my calculator, so I'm just gonna have to add them by hand. Oh, but actually it doesn't matter the radius, it's way too small. So let's just forget about it. Times 3.6 times 1, 2, 3, 4, 5, 6, 7. It's about 7.17. What do you want? What do you want from me? 2 pi? Yeah, that's exactly what I did. Did I times 1 too much for times? What if I times my answer by 60? 1, 2, 3. 1, 2, 3. Okay, that doesn't even work. That's what I did though. I don't know what he wants. Right, that's what I did. So let's just write it down in case we need. It's about 3,100. Cool. Yeah, my 7 was a dumb answer anyway. Why would it be 7? Calculate the gravitational field strength at a point in the orbit of the satellite. Gravitational field strength GMM divided by R squared. Do we know the mass of the Earth? We don't. I guess we don't because it's proportional. It's acceleration, right? And we know v squared. Is it just v squared divided by r? Could be. V squared divided by r. Okay. We're still on the easy thing and I can't do any of the questions. 1/4 of the way through, a car enters a roundabout with a speed v. The dotted line shows the path of the car. The road is slightly banked at an angle to the horizontal. The coefficient of friction between the tires of the car and the road is oomph. When oomph decreases, which of the following changes could prevent the car from slipping away the roundabout? Increase the angle and decrease the speed. C. Why is this not the first question that I get? This is the easiest I've ever seen. A car makes a U-turn on a flat horizontal road at a speed 9. The inner radius of the U-turn is 4, outer radius 6, 10. 6 is the subtraction, which I went too fast in doing. What is the best estimate for the minimum acceleration of the car when making the U-turn? Flat horizontal road at a speed. Okay, so we have v divided by r. Do we know the size? Do we just have to use 10? That's not realistic. That's not realistic. If we use 10. 9 squared is 81 divided by 9. It's 9. So technically 9. But the closest you can get is this. So I'm going to go with C, though I don't agree with it. I think the largest radius. Oh, is it 10? Yeah, 10, not 9. Anyway, an object with a weight W connected to one end of a rod, negligible mass, rotates at a constant speed in a vertical plane. Okay, we're in vertical again. When the object is at the top position of the circular path, the tension on the rod is 0. What is the magnitude of the tension at the bottom position of the circular path? Where is that tension is 0? The magnitude of the tension at the bottom. It's probably well, it has to be more than W, right? Well, if it's 0 at the top, so weight is mg, so it's gonna be its acceleration. It's proportional to the acceleration of this thing. Or is it just equal to W? Because it's an inward. How does this even work? Let's just go with a C. Okay, at the top position, tension plus W equals F centripetal. And tension equals 0, so W equals centripetal. That's what I had. At the bottom, T minus W equals centripetal. T minus, yeah, because minus. Since speed is constant, F equal, therefore the tension at the bottom, T equals 2 W. Okay. Oh, we were looking for the tension as well. Okay. This is a weird topic, which I clearly don't understand. A space station X orbits Earth with orbital radius r. State Newton's universal law of gravitation. It's the GMM there, r squared, which you can define all the variables. Explain why an astronaut in the space station feels weightlessness, because the space station is in gravitation, is in circular motion, I guess you have to say. Therefore what? It's accelerating at the rate of the acceleration, you know. Centripetal force is the gravitational force between Earth and the space station. I had that. Both the astronauts and the space station have the same acceleration. It's the same thing. Oh, and the space, no, it's not. Acceleration and the gravitational field strength. What? The acceleration is the gravitational field strength at that position. Therefore, what? You don't feel. The space station changes position so that the orbital radius is this. Explain how the gravitational field strength at this new position compares to that. It compares gravitational field strength. It compares by 1 over r squared. So 1 over 4. Is this it? 1 over 4? 1 over 4. Another space station Y with a smaller mass orbits Earth at the same orbital radius r. So let's see, another space station Y with a smaller mass orbits Earth with the same orbital radius r. Let me draw it. I don't know why I can't understand what I'm reading. Y and X. Oh, okay, I understand. Compare the orbital speed of Y to the orbital speed of X. So orbital speed is dependent on a r squared, therefore gm over r squared. So it's the same orbital radius, but it's has a smaller mass. It's gonna be square roots or something like that of the thing. Yeah, square root of what we had. 19. An atom is being modeled with an electron, seeming to be orbiting a nucleus in the first energy level. It's going to be rough. Estimates. With a speed of 2.18. The orbital radius of the ground state m is given by this. The energy level. Determine the charge of the nucleus. Determine the charge. Who do you think I am? How can I get the charge right now? Wait, the charge of the nucleus. The atom is being modeled with an electron. The charge of a nucleus. Why are we talking about charge? Do we have to use the KQQR2 using the electron Maybe if we use the electron thing in the data booklet as Q2 and Q1 is the unknown, and make that equal, we know R squared, we can make that equal to the force, the centripetal force, which we can calculate because we have M, we have R, and we have V squared. Okay, so I guess that's how you do it. Let's just see. What's EQ, my guy? Oh, yeah, E is what I said in the data booklet. Equals mv squared r. Okay, that's exactly what I said. Next, the electron moves to the second energy level where it orbits with a kinetic energy of 5.44. Explain whether the centripetal acceleration increases, decreases, or stays the same. It probably decreases because we've increased the radius. Let's just go with increase. Let's decrease. Okay, correct. There's an increase before, because that's not what I meant. Calculate the orbital radius of the electron in the second energy level, or the orbital period. Oh, we have A. Do we have A? Do we have to find A? To get this. If we have V, it also helps. Well, we have the radius, okay. We have the kinetic energy. So if we have the okay, we have the mass, the kinetic energy, so we can get the velocity, first of all. If we have its velocity, we can divide that by r to get A, and A is equal to 4 pi squared r divided by t squared. Therefore, we can get t, because it's all constant, and we all know what these mean. Or could have been squared to make things faster. 4. So this is what I said. Wait, let me see. Okay, yeah, mv squared. Wait, was there an easier way? Yeah, true that you don't have to do the whole big equation. Could have been a bit faster. Satellite A of mass m orbits a planet with an orbital speed v. A satellite A of mass m. Satellite A of mass m orbits a planet with an orbital speed v and an orbital radius r. Another satellite B with mass 3m orbits the same planet with the same orbital speed. Knowing that the ratio centripetal force of satellite A and centripetal force of satellite B is 1/3. What is the orbital radius of satellite B? Wait, satellite A of mass m orbits. So mass is tripled and orbital speed is the same, right? So if mass is tripled in B, with the same orbital speed, not the same orbital radius, there's probably going to be a square root of something, though. Oh no. So what is proportional to what? F, centripetal force, is proportional. Is it proportional to mass in any way? Yeah, it is, right? It seems to be. Oh no, it wasn't in the other thing, even though it should be. Because big M, small m. Oh No, it's small m, so it's not. So mass doesn't change. The same planet with the same orbital speed. So then it's just radius, and F is proportional to. Wait a second. R should be proportional to the orbital radius. What the? I didn't mean to mute. Sorry. What is the orbital radius of satellite B? Wait. It should be 1/3. It should be the opposite. Double. Wait, how? It has to be C then. Okay, C. C, yeah, I see. Now wait 2 seconds. I need to. The sky is really nice. If you want to see it, if you live anywhere close to where I live, you know, it's, yeah, really nice sky. Anyway, this was correct for some reason. Now next, planet X has 5 times the mass and 8 times the volume of the Earth. 5 times the mass, 8 times the volume of the Earth. So M5 and 8 the volume though. What is the gravitational field strength on the surface? So volume is proportional to R cubed, right? So if it has 8 times the volume, it has 8 squared the radius cubed. So 8 cubed, what is that, 256? Or 512? There's a 64. It's 2 to the 2 to the 9, so it's 512. 512. Assume that both Earth and planet X are spherical. What is the gravitational field strength on the surface? G equals M. G equals big M divided by, okay, big M. 5 times the mass, so 5 divided. What? Why isn't it? Has 8 times the volume. Shouldn't it have? No, that's square root 3, 2. So C. Did the wrong way around. Not. It's. I swear to God. Where did you get this shit from? Oh, it's R squared. God damn it. A roller coaster passes a vertical loop in a constant gravitational field. Friction and air resistance are negligible. How do the kinetic energy of the roller coaster and the normal reaction force acting on the roller coaster compare at point X and Y? Kinetic energy is... Okay, so there's no motor or something, right? So the kinetic energy is going to be greater at X than Y. The normal reaction force it's probably more at Y than X. So A. Greater at X. What do you want? Oh, because there's mg. There's mg. It's greater kinetic at the bottom of the, yeah, hence B and C are rejected. Okay. Normal reaction force by the track contributes to the centripetal force needed for the roller coaster to move along the loop. Normal reaction force by the track contributes to the centripetal force needed for the roller coaster to move along the loop. Since centripetal force increases with speed, the normal reaction force is larger at the bottom of the loop when the speed is greater. Centripetal force increases with speed. As the centripetal force increases with speed, the normal reaction force is larger at the bottom. Oh, since it increases. Since when does it increase with speed? I guess it does. Okay, okay. Okay, we'll take that, whatever. Question 23. Ugh, look at these questions. We're entering medium territory and I'm not happy about it. The moon orbits the Earth in a circular orbit. Does it now? Explain why the centripetal force is needed for the moon to be in its orbit around the sun. Because you want... explain why the centripetal force is needed, because the moon is in orbit. So... or else the moon would fly away. Because the radius is constant. What do they want? Without force towards the center, the moon will move in a straight line. This is weird, logically, because it says explain why the centripetal force is needed, but it depends which lens you're looking from. So it doesn't make much sense to me. Identify the origin of this force, the Earth's gravitational force. Yeah, of course I would specify gravitational force. Show that the orbital period t of the moon around the Earth is given by this. So all you have to do is rearrange the equation that states you're gonna A is G, so you're gonna write mg, big G, m divided by r squared. You're gonna make that equal to 4 pi. No, you're not gonna do that. To 2 pi r. 2 pi r divided by big T. And if you rearrange everything, you basically don't get what you do get, but with a slight problem, because where does the square root come in? The orbital period t. 2 pi divided by t is omega. Oh, that's v, and that's squared, this whole thing. Okay, so now, because it's squared divided by r, so this just goes away. And we've got it, because it's squared. With the r as well, so that should work. So, right, let's just see the derivation. Yep. T squared, yep. Yeah, I took a long way. Somehow I took another 2 equations which weren't needed. Knowing that the mass of the Earth is this and the orbital radius is this, calculate the orbital speed of the Moon around the Earth. So that's just subbing in. Is that just subbing in? So you know the mass of the Earth. So you can get the centripetal acceleration because you know mass and radius. So you can get g using gm divided by r squared. Using g, you can equate that to v squared over r, so you're going to times by r and square root the whole thing. Let's see if they times by r. Where are they? bi. What's the point of using the time period? I mean, you can, but oh yeah. What? What? Wait, what did they ask for? The orbital speed. Is the orbital speed the velocity or the omega? Because that changes things. Yeah, v. V is not omega. So what are they on about with the whole thing? Next, total solar eclipse seen when the sun, the moon, and the earth lie on the same line, the moon in between the sun and the earth. Okay, knowing all of this stuff, determine whether the sun or the earth exerts a greater gravitational force on the sun. So you can use the gmm divided by r squared in different directions. Let's see, the mass of the sun is pretty big, but the distance sun-moon is this. So let's just approximate 11 times 2 is 22, so that would leave 8, 10 to the 8. However, with the moon, the distance, where's the distance? Moon, Earth. Was it somewhere before? Where's the distance? Oh, there, the orbital radius. Okay. So 8 times 2, 16. Mass of the moon. Mass of the moon. I want the mass of the. Oh right, there's the mass of the moon, but it doesn't matter, right? Mass of the Earth is 10 to the 24. It's 10 to the 8. And before we also had 10 to the 8. However, yeah, it should be a bit more. The Earth should be more. I feel like my calculations were wrong. This approximation doesn't work. Does my sound still work? Yeah, they do. Oh, so it is relatively close. What do you mean? What do you mean? This? Oh, because the bottom is squared. Yeah, okay, so for my approximations, it should have been around this. So and it was relatively close, and so I'm guessing it was correct. But that's weird. Why Why doesn't the moon just leave if that's the case? Total, so we just did that. Explain why the sun doesn't pull the moon away from the earth. Yeah, why? Yeah, I don't know. I don't know why. Because it has a velocity, because it has a centripetal force as well. The moon has a centripetal force. No, because it is equal. So both the Earth and the moon orbit. Both Earth and the... Oh right, they orbit the sun. But now what? The moon remains in gravitational orbit around the Earth as both travel around the sun. The moon and the Earth experience the same centripetal acceleration while orbiting the sun together. Alright, they have the same attraction. That's valid. A ball is tied to a 10 centimeter rope and rotates in circular orbit. No, in circular path, starting from point X with a linear speed of about the rope cut after 2 seconds, at which time the object step 1y is shown in the diagram. Is the it's probably going to be, well, it's going to be this or this. Angular displacement, or between X and Y. So basically it's going 20 to, so 40 centimeters, it's a 20, so you just do the percentage. It's probably going to be 2 radians, I don't know, but I know how to do it, but I don't want to calculate, yeah. 4, sad. So it's D. What? Direction of motion? It's going from X to Y though. Wait. It starts at point X. The rope is cut after 2 seconds, at which time the object at point Y, as shown in... At which time? At which time the object at point Y is shown in the diagram. Doesn't it just do that, and then gets cut? Why would it ever go in the opposite direction? Okay, it's probably something with the question I'm not understanding, but it's not how things work. A roller coaster car with a mass 80 kilograms moves on the track shown the diagram starting from point A. At points B and C, the track approximates a circular path so that the radii at B and C are 12 and 18 respectively. Compare the normal force exerted by the track on the car at points B and C. At points B, C, the track approximates a circular path. So the radii at B. So normal force should be greater at B than C. Draw a labeled free body diagram of the car at point C. So it's going to be mg going down plus centripetal force going down as well as normal going up. Alright, you can't label centripetal. And it should be a bit bigger. I forgot. Wait, however, A, I didn't check. B is bigger than C. Yep. Calculate the maximum speed of the car at point C so that it could remain on the track. True, because it might just leave. Let's see. We have the radius, 18 centimeters. We have, we're not looking for. We have its acceleration, which is mg, which is 9 point. It's not 9.8. It's per. It's all just 80 times 9.81. So 80 times 9.81 times by 18 square root square root 13. Is that it? Okay. Mass M is moving on a circular path at the end of a rope of constant length. The centripetal force acting on the mass F. Centripetal force acting on the mass is F. The frequency of the motion is gradually increased. Which graph correctly shows the change of centripetal force as the frequency increased? Frequency, centripetal force, the frequency. Oh, frequency is omega, isn't it? The frequency is omega. Well, it's not really omega directly. Or is it? More or less. Like omega 2 pi, frequency times 2 pi is probably omega. Something like that. A mass M is moving on a circular path. What do they want? Oh, of centripetal force. Omega squared, so it's probably going to be A. Let's go with A. Yep. A roller coaster of mass M approximates a circular motion at point A, as shown on the diagram. The circular radius of the track curvature at point A is R, and the track exerts a normal reaction force Fn on the cart, which expression gives the linear speed of the cart at point A. Circular radius of track curvature at a point A. So it approximates circular motion, so it should be more. How can it approximate circular motion? Practically, I mean. Reaction force Fn on the circular radius of the track of on the cart, on the chart. Which expression gives the linear speed of the cart at point A? So linear speed equals acceleration times r. So Fn times r. Wait, let's think. Fn divided by m. D. But why? Centripetal force on point A is the vector sum of the weight of the cart and the normal reaction of the force on the track. Oh, yeah. I hate this unit. Planet X has radius R and the planet gravitational field strength at the surface of planet X is G. What is the ratio of the gravitational field strength at the surface of planet Y, which has a radius of 0.25 r and a density of 3 pi, to that at the surface of planet X? Has a radius r and a density rho. So it has 3 times more density. And, whoa. So the radius is this. So what do we want? Gravitational field strength. So we're going to use the gm divided by r squared equation. So 0.5 is going to be squared. 25, sorry, is going to be squared. And m. Now we need to figure out m. It's going to be 0. It's going to be the radius. It's going to be the radius to the 3. So 0.5 to the 3. 25 to the 3. Times by. Wait, density equals. Times by the density. So times by 3. So in the end, we get 0.25 times 3, which is a. Ah, finally some correct answers. Almost halfway. A proton and another object with charge plus E exert an electrical and gravitational forces on one another. To the nearest order of magnitude, what mass must the object have to be so that the net force acting on it is 0? Mass m, charge E plus, proton. So that didn't, okay, so they're repelling, but they're attracting. So you want, its mass to be equal in order of magnitude. Probably a big mass. That's what I can tell you. This sucks. Let's ignore the constants. We need all the constants, don't we? The proton thing and what's plus E? Plus E, so proton is at plus E, so E squared. Why don't we have a distance between them? Okay, I don't know. Let's guess C or D. Yeah, so you have these two equations. GMMP equals K solving for M. K E squared GMP. Yeah, rounding to the nearest order of magnitude. Oh, I didn't. Okay, so I was correct, but I just couldn't be bothered. And I guess that was a good choice, wasn't it? What's MP? Mass of a proton. That was a good choice. State Newton's law of gravitation is, you can just define the variables again. This thing. Yeah, except formula, if all terms are defined. A geostationary orbit is a special orbit in which satellites follow a circular path and remain above a fixed point above the surface. A satellite's orbit in geostationary orbit at constant speed v and orbital radius. Does my mic still work? Let's check. Yeah, and orbital radius r. Constant speed v and orbital radius r. A satellite in geostationary orbit at a constant speed v and orbit's radius r. The mass of show that v equals this. We can do that. Substituting this thing, this thing, this thing, this thing, this thing. Fair enough. We already have the satellite's orbit. Use this information to estimate the mass of the Earth. Use this information to estimate the mass of the Earth. So we know the radius. You have to use the 365 days thing. Speed. Yeah, you have to use the whole 365 days. Wait, do you even? 2 pi r. Yeah, you do. Exactly. So nothing new. And now we're halfway through. A toy of mass m is attached to a rod of length L and undergoes circular motion in the vertical plane. The radial force F of the rod is constant. What is the ratio of linear speed at the top to the linear speed at the bottom of its path? The radial force. These terms in this unit. Well, one is minus and one is plus. I don't see the point of having a square root, but if there's a square root, there's probably because there needs to be. So I don't know. This door keeps opening. What is the ratio? So let's just think F. A, probably not. Yeah, probably not. Okay, that's double wrong. At the top, the centripetal force is F plus mg. At bottom centripetal force. Why is it? But this should be much more at the bottom, isn't it? Well, tension is more. Isn't centripetal force tension? If you had a thing on a rod, we arrange the above equations for the required ratio. The centripetal force is F plus mg. The fuck was F though? The radial force. F. The radial force. The radial force. So the radial force is that outwards. The 2 points masses 4m and m are separated by 30 centimeters as shown. At point A, the net gravitational field due to the point masses is 0. Yeah. What is the distance between 4m and A? So at a point, gravitational field strength equals m divided by r squared. Okay. Oh no. I was holding my pen And now I'm black. Scheiße, man. Oh, that's disgusting. It's not gonna come off in ages. 4m. Let's write 4m divided by r squared equals m divided by r squared. That gives us 4m equals m. That's a dumb thing to write. You want the net gravitational field. So you want G and G to be equal. Oh, but F, R, and R aren't the same, because R is 30. If we make this R, then it's going to be R, and then 30 minus R. So, we're looking for R, are we? Therefore, we have, so we get rid of the m's. We have R squared equals 430 minus R squared. It's ridiculous. Now we have a shit ton of variables. R squared disappears, so 1 equals 1 equals, oh no, you get a quadratic? Do we have to solve the quadratic? Yeah, this. Oh, right, it's a 2. We could have just gone smarter way to do it. Okay, I admit. Should have seen the squares. A car enters a horizontal circular roundabout as shown with a speed of 35 kilometers per hour. The radius of the roundabout is 15 meters. State the force which provides the centripetal force of the circular motion. The car. Friction. Friction. Calculate the minimum coefficient of static friction between the tires and the car and the road. Car safely complete its motion around the roundabout. Coefficient. So we know that the oomph times R equals F. Oomph times R equals F. R. No, it's not this. It's not this. Okay, show me. I concede to your tricks. The speed of the car is this, which is this. So you get the speed of the car. Yeah, that's true. The frictional force provides the centripetal force. Therefore, you equate this to, so it was mg. Okay, I was on the right track. I just gave it up too quickly. Calculate the minimum coefficient of static friction between the tires of the car and the road for this car to safely complete its motion around the round. That's what we just did. Say it's an Explain any changes in your answers to part B if the mass of the car increases. That would change. That would decrease. Decrease. The road is banked at an angle. That would decrease. No, that would increase. That was decrease. Or the speed of its car increases. That would, okay, basically this would make it better. This would make it worse. This would make it better. This would make it worse. No change. Yeah, but we literally have. Oh, this cancels. Decrease and increase. This diagram shows the gravitational field between two masses, M1 and M2. Which is correct? The two masses are equal. Let me think. No. So there's more line concentration. Two masses repel each other. Yeah, how is that working? What does it look like they're repelling each other? That's wrong. M1 is greater. D? Yeah. Oh yeah, true, because also it's there. The centers of three masses lie on the same line. The centers of three masses lie on the same line. The center of the masses are separated as shown. The gravitational force is 0. The value of D is 1/3 of x. 1/3 of x. What is the ratio? M1 to M3. The net gravitational force on M is 0. Let's think. What is the value of D is what when the value of D is 1/3 of x. So what we're gonna do is the equations we've been using pretty much, where D is R, or D is, yeah, D is R, D replaces R. So you have M1, M2 divided by D squared. Let's just write it down to make it clearer. Is equal to, because there's 0 resultant force, M2 M3 divided by, M2 cancels of course, divided by x minus D. Let's just write that. Now we know that D is 1/3 of x. So D, actually we could have just written 1/3 of x. So 1/3. And 1/3 squared, so it's going to be 9m1 is equal to m3 times just m3. What is the ratio m1 to m3? I have 1/9. What happened? What happened? What happened? X should be 1. So just 1/3 maybe? 1/4. Oh, did I forget to another change? Yeah. X/3. Oh, 2/3. So wait, let's just make this 2/3 in C. That would be divided by 4 and 9 here. Yeah, so the 9's cancel. get 1/4. Sure, it wasn't x wasn't 1, it was I used the whole distance instead of using this. So 1/4. A mass spectrometer is a tool that uses a magnetic field to determine the mass of a moving charged particle. An alpha particle with speed this enters a region of magnetic field directed into the plane of the paper. Suggest why the alpha particle undergoes circular motion inside the magnetic field. Because it experiences a force. Because it's positive. So this is moving. The field is into the page. It's moving this way. This is going to explain. Why the alpha particle undergoes circular motion. It's because there is the rate of change of velocity caused by a change of direction. Is that what they want? Particle experiences magnetic force. The alpha particle force perpendicular to the velocity, which is the condition for circular. Yeah, okay. Yeah. Why do you need the first one? Okay, circular motion is the velocity. Okay. Next, why the centripetal force does no work? Because there's no displacement. Correct. Vector displacement is 0. That's correct. On the diagram, draw an arrow to represent the path of the alpha particle inside the magnetic field. It would be like this. Yep. Oh, exiting the magnetic field. Why can't I do a full circle? How do you know? Does it say? Oh, it's a spectrometer. It's also spectrometer. On the diagram, no, state the charge of an alpha particle plus 1 plus 1. The radius of the path of the, no, plus 2, because it's 2 protons and 2 neutrons. The radius of the path of the alpha particle is determined to be 15 centimeters, and the magnetic field strength, this. Calculate the mass, Tesla's, calculate the mass of the alpha particle. Expressing your answer to the appropriate number of significant figures. Calculate the mass of this particle, experiencing your answer to the appropriate number. Did you just calculate the mass using U? So magnetic field strength. Okay, is this part of another topic? Let's just see. Magnetic field strength. Magnetic, yes, you needed this QVL. You know Q. I guess you know rearranging MQRVV. That makes sense. Okay, that makes sense. I just couldn't be bothered to look at the other pages. This would be in topic 5, this 5.4. Planet A has a gravitational field strength G at its surface. Planet B has twice the density and twice the radius of planet A. What is the gravitational field strength at the surface of B? Twice the density and twice the radius. If it has twice the radius, it therefore has a root. Wait, let's think. Twice the radius. Therefore, its volume is times by 8. If it has twice the density, then it has 8 times 2 has 16. 16 times the mass. Is that potentially correct? Making C a wild guess. Yeah, C. Divided by 4. What did I forget to do? Sure, sure. Satellite A and B orbit the same planet of mass m. Satellite A has a mass of 3m and is located at a height r from the surface of the planet. Satellite B has a mass m and is located at a height of 2r from the surface of the planet. What is the ratio of the centripetal force acting on A and the centripetal force acting on B? So, we have R and we have M. What else do we have? This is so F equals MA. It's one thing. So we have MGM divided by R squared. Oh, that's literally just the gravitation thing. So the big mass. Satellite A3M is located at height r. Satellite B has a mass m and is located at a height 2r. So let's just ignore the m's, because I don't think, remember, it doesn't matter. So if we ignore the m's, we can still use the r's. Height r from the surface of the planet, height 2r from the surface of the planet. And if it's inversely proportional, and let's say it's squared, but it's not squared. So that doesn't make sense to me. But looking at the answers, I'm gonna guess that it's something like B. Let's see. It was A. It was either A or B because the IB are not creative in that way. Let's see why. Each the sum of the radius of the planet and the height from the surface, thus 2r and 3r. Oh, you had to use... Yeah, see, the masses don't matter. That was cheeky of them. CD store on the surface, on its surface, on a number. A CD stores data on its surface on a number of concentric circular tracks of different radii. The radius of the first track is 25 millimeters. That of the last track is 60 millimeters, as shown in the diagram. The data from the CD is read by rotating the disk under the laser system where the tangential speed is always 1.5 for the date track being read. Which of the following is correct about the angular speed of the first track W and the angular speed of the last track W2? The angular speed and the angular speed of the last track. 60 rads per second, same as W1. Oh, because it's smaller. Okay, the first track and the last track. The angular speed is going to be the same. Shouldn't it be the same? Same as W1. Now, the first track, it's 1.5 meters per second. So, where's the conversion thing? Oh, it's still omega is dependent on R. Oh, but velocity increases, so it doesn't matter. 1.5, then 1.5 divided by 60. What is that? 0.15. 5/2. 2.5. Let's say C. Ay, 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 ay. Oh, it's constants. Oh, right. Okay. I missed the part. Yeah, of course it has to be constant because it's a CD thing, so I can't read. Yeah, that changes things. So, but was it? Oh, it says B, right? How is it 60? Did I do the division wrong? Yeah, I divided by 60. Oh, it goes from here to there. Okay, okay. The rotor ride. Ow. Ow. The rotor ride in an amusement park. Um, I just accidentally. Sorry about that. A rotor ride in the amusement park consists of a vertical cylinder that rotates around its axis. Its floor drops down when it rotates fast enough so that the person inside is held against the walls. The walls are made up of rubberized material. It's always that question. It's always the same thing. Explain the terms of in terms of forces how a person can remain suspended against the wall without falling when the floor is dropped. So as long as the coefficient of static friction times by the normal reaction, as long as the friction force down basically is equal to the weight. Wait, what does it say? What was the minimum? Okay, the normal force provides a centripetal force. The minimum speed is a required relation to speed, linear speed. Friction balances the weight. So you need yeah, the centripetal and the friction. Show that the maximum speed of rotation for the person to remain at rest relative to the wall is given by this. So let's see, radius of the cylinder and coefficient of static friction. The maximum period of rotation though, because why can it be bigger? The rest relative to the wall is given by this. So let's just, so R we said was the centripetal force, therefore static coefficient of static friction wait, the coefficient of static friction Gotta times that by something else. Hmm. This question. Relative to the wall is given. Show that the maximum period of rotation for the person to remain at rest relative to the wall is given by this. Maximum period of rotation for the person to remain at rest relative to the wall. You have to use the static. Let's just see what's given to our temptations. So F equals, okay, centripetal force. So that's Fn, normal reaction. Therefore, where did you get that? No. Oh, did we have a pre-existing formula? No, we didn't. Why would you do that though? What's FF? Friction. But you have to put the static on here. What even is this static thing? So lost. Okay, the normal force is the centripetal force. Okay. The frictional force is given by this times normal force, yeah. Then the frictional force, since the frictional force is in equilibrium with the weight. So mg equals the in equilibrium. God damn. Oh, you're okay. Mg, the weight. But why is it? Oh, yeah, mg static. Okay, I guess. Then this equals. That's what you just did, though. What the hell? What the hell? This is not funny. The coherence stuff, I calculate the speed. This is just the speed. Well, if you have the time period, if you have the R, then you've got your thing. Sorry to say, but it's just substitution. To make the ride more exciting, an idea for an axis. Oh no. Try fully for a person at A. Uh, Normal. Um, um, G. Frick. You'd put friction up. Seems like a weird place to put it, and I feel like there wouldn't be something there. But let's see. Oh yeah, there is. The cylinder is tilted a full 90, so that its axis of, okay, deduce whether the minimum speed of rotation of its rotation is greater than or less. The minimum speed of rotation should be greater. Or maybe not. To be honest, I don't know. I hate this. Ugh, I hate this question. How many worded questions are there gonna be? I can't wait for these. To be honest, I cannot wait at all, so I'm just gonna do them. A cart of mass m enters a smooth vertical loop of radius r and horizontal speed u at the bottom of the track. The car just manages to stay in contact with the track at the topmost point of its path. Its speed at the bottom of the loop u is given by k. A cart of mass m enters a smooth vertical loop of radius r with a horizontal speed u. Do you use energies? Let me use energies. I'm gonna say half mv squared is equal to gm no, what is it? mgh. Mass cancels. G is 9.81. Height is 2r. So it's 2 times 9.8, 2 times g. 2 times g square root ud. Who? Yeah. There's no potential energy at the bottom, is there? There's no kinetic. Oh, there is. Nobody said just. Centripetal force at the top of the loop equals plus mg2r mv squared. Yeah. Centripetal force at the top of the loop comes from the weight, the cart, and the contact. Because the question says that the car just keeps contact with the track, you can assume that the normal reaction force is effectively zero. Writing the law at that point gives mg plus n equals mv blah blah. Mg plus 0. Substituting this result into 1 gives you mg plus n. I can't with this. I can't. What? Okay, more multiple choice. Another bullshit question. The tip of the second hand of the clock moves from the 12 to the 6, 180 degrees, marking with a tangential speed of 2 centimeters per second. Which of the following is correct about the angular speed of the centripetal acceleration and the centripetal? So the angular speed. So 2 centimeters per second. Let's just make it 0.02 meters per second. So this divided by r is the thing. What's fucking r? Okay, I guess we just need to make it that's 30 seconds. So it takes 30 seconds for this to go there because it's clock. So, well, technically we can't assume, can we, that the clock is on time? We're not even on time, just like works. How can we assume that? Marking, so yeah. What are we dividing by 30? Pi. Pi divided by 30. There we go. Centripetal acceleration shall be 2 squared 4 divided by r. 2 divided by this thing. It's gonna be 60 divided by pi. If you're gonna write 60 divided by pi, 4 divided by 60 divided by pi equals pi divided by 15. Thank you for being an answer. D. Finally, a good question that doesn't require actual physics. A mass M attached to a spring is moving in a horizontal circular motion as shown. The tension on the string T and the angle with its vertical is theta. Which of the following statements are correct for this motion? Centripetal force equals mg tan theta. Yeah, remember this is just a thing that it's mg tan theta. The tension is no. Okay, centripetal force probably mg tan theta. Total gravitational kinetic energy of the mass is constant. Should be the case. The rope is cut, the mass will fall downwards. That's false. Let's just say 1 and 2. Yep. Mass Y is attached to a rope. A mass Y is attached to a rope. Attached to a rope is moving in uniform circular motion on a frictionless table as shown on the diagram. Circular paths of constant radius r is shown with the dotted line. The mass X is hanging from the lower end of the rope. Masses X and Y can be adjusted. What independent adjustments to mass X and Y could produce uniform circular motion? Lower speed v, but with the same radius. That can be what independent adjustment could produce uniform circular at lower speed v. So an increase in y and x and a decrease in y and x. Oh, you want a lower speed. Uh, maybe that's true. An increase. An increase. No, decrease. Well, it's either D or A. So D. Here we go again. Centripetal force spread by the weight of the hanging mass. For X equals YV squared. Yeah, to maintain the same radius with a decrease. Oh, you need to maintain the same radius. Okay, I will take that and go to the next one. Find gravitational field strength. It's always the same. The Earth's average radius is given by 6.37 times 10 to the 33. Calculate the height above the Earth's surface at which the gravitational field strength becomes half of its surface value. Calculate the gravitational force acting on a satellite at mass m. Maybe I should do B before doing C. Or maybe I should skip to this one. A small ball of mass m is attached to a string and moves in a vertical circular path. Radius r. What is the minimum velocity v at the lowest point of the path for the ball to continue moving in a circular path? At the lowest point of the path for the ball to continue moving in a circular path. So at the bottom, the path, the velocity, so a, wait, what is the minimum velocity, lowest point for the ball to continue moving in the, so acceleration, which is g. Is it g? No, it's more than g. So you want g. I guess it is. Oh, maybe you have to say, okay, g is because it's the minimum when g equals this. So assume this times by r square root. There's no way that's correct. It's also not one of the answers. Um, At the top, the minimum speed. Okay, let's read. To calculate the minimum value of velocity at the lowest point, we need to calculate the minimum kinetic energy. Oh, it's kinetic energy. At the lowest point, the total energy is only kinetic, and is and that the potential energy is zero. Lost at the top, the speed of the cycle occurs when the centripetal force equals weight of the ball. Centripetal force equals weight of the ball. So mv squared divided by r equals mg, giving v squared equals gr. Total energy at the top equals kinetic energy. Et equals this plus this, where h equals 2r. Okay. Sure. Two planets, X and Y, have the same density. However, the radius of planet X is larger than that of Y. Two satellites with equal masses A and B orbit X and Y respectively with the same orbital radius. Which of the following quantities is smaller for satellite A? Which is it? Oh god. No. Um, let's just check. Right, okay. Two planets X and Y. Let me draw because my brain is dead. Have the same density. However, the radius of the planet X is larger than that of two satellites with equal mass and X and Y respectively with the same orbital radius. Which of the following quantities is smaller for satellite A? Well, technically, there's an orbital radius. Yeah, that's your orbital radius. If they have the same density, but one is larger, they have the same mass. No, do they have the same mass? Oh no, they have the same density. Okay, so density times volume. But is this one of these radius again? The radius of planet X is larger than that of Y. Therefore, it has more mass. Two satellites with the same. Which of the following quantities is smaller for satellite A? Well, the orbital speed is going to be greater for satellites with the bigger mass. Satellite. However, radius of planet X is larger. So A is going to have a smaller A and B orbit X and Y. Oh, X is the one with, so A goes with the one with the bigger thing. Shouldn't have a smaller, if they have the same radius, it needs a smaller, a bigger, oh no, it needs a bigger speed. A bigger centripetal acceleration, probably bigger, but a smaller orbital, I'm guessing B, because it's, yeah, B. Trapeze artist, ah yes, multiple choice. Wait 2 seconds, I need to fix something. My Wi-Fi is dying. Why doesn't it work? Combined mass of the artist and swing. Position A to C. Kinetic energy, isn't that okay? MGH. What? This length of the rope of the swing is L. Of the swing is L. The tension at position B. Okay, so you have the tension. What can you get with the tension? Well, you need its speed. If you want its kinetic energy, you're going to need its mass, which we have, and v squared. I guess you can do v squared at this point equals a times r. What is a though? You have nothing in this thing. You have the length and the tension. This is horrible. You have the length and the tension. Right, you know the tension is, yeah, tension minus 700 will give you a centripetal force. So we have centripetal force. Do we have R? Oh, R is L. And mass is 700. 100. Oh, and mass cancels from a v squared. So yeah, it does work. It's A then. Or wait, yeah, A. Uh, uh, no, wait, 2 seconds. So now we back. We're nearly there. 8 more questions to go. So, first of all, when the car. Oh yeah, so we were doing the roller coaster. Roller coaster goes around the inside of a loop of radius r, shown in the diagram. The combined mass of a car and the passenger is m. When the car is at its highest point, the normal reaction of the track on the car is equal to half of the weight of the car and the passengers. Which expression gives the kinetic energy at the top of the loop? Again, the normal reaction force on the track is equal to half of the weight of the car and the passenger. So half the weight of the car and the passengers. Do we know the m? So m over 2 is equal to the normal reaction, which is equal to the centripetal force. Uh, equal to mv v squared over r to mv, which m is it? Yeah, mv squared over r. So m cancels 1 over 2 equals v squared over r. Now what do we want? That's a fact. So 2. So r over r equals 2v squared. Big R, right? The kinetic energy of the center, kinetic energy of the top of the loop. Kinetic energy at the top of the loop. So wait, let's just write kinetic energy. The bottom is equal to the kinetic energy the top plus mgh. Okay. So basically, oh, 2v squared at the top. So I got the velocity of the top. So let me sub in that. That's m r over 8. Yeah, it's already wrong. I know it's half of this guy, so 4, something like that. M and then v squared is at the bottom. Let's see what they wanted. The velocity. Okay, 0.5. And the total normal force on the track of the car. So mg. Oh, we have to add mg. That gives you this. It's ek equals this. Then ek equals. Oh yeah. I don't need the whole bottom thing. This is like, once again, horrible question. Well, no, it's a good question, but not for me. A 200 is moving inside a horizontal circle. Is moving inside a horizontal circle. Shown with the dotted path in the diagram. The diameter of the ball is 40 centimeters. The angular speed is 4 pi rad s. What is the magnitude of the ball's centripetal acceleration? So the diameter is 40. Put this towards the center. So do we need trig? So we can, no, we can't use trig. I mean, we could theoretically, but need the depth. You have its angular speed, so you basically just need r. You need this. Um, oh, but it's a semi. That's a diameter. We don't even know that that's a diameter. Let's see. Yeah, it cannot be Benjamin because we don't know if it's a diameter. Even if it was, I don't even know if it's possible. This is not multiple choice. Oof, this is hard. It's the hardest. Wow. Wow. Full hard. Never seen that before. Okay, where were we? A satellite X is in a circular orbit R. Um, let's draw that. Satellite X is in a circular orbit of radius r with a time period t around the Earth. What will be the total? What will be the orbital radius of satellite Y traveling in the circular orbit with a period 8t? So clearly radius is proportional to t squared. So if t is 8, then um, that's a problem because um, we have no square roots here. Let's see. Orbital radius of satellite Y. Ah, no, it's not. It's r squared. Oh, they're just proportional. So B, that would be, there's no way it would be here though. It can't be B. Let's see why. C. Two formulas are needed. This and the centripetal acceleration. This. Rearrangement of Kepler's third law, G equals A, which relates orbital period with radius. G equals A, fair enough. So G equals A. Wait, T. How did they just isolate T squared that quickly? T squared does indeed equal all of this divided by GM r squared. So yeah, that is correct. Now T. Oh, so T squared. Oh, isn't that in one of the? I thought it was in the data booklet. Some. No, maybe not. Um, um, how's the chat doing? It still works. Yeah, it does. Yeah, it does. Okay. That's sad. Why didn't that just work though? I guess, yeah. A satellite of mass m in an another. A satellite of mass m is in an orbit at height h from the surface of the planet m. The centripetal force acting on the satellite is F, and the linear speed is W. What is the new centripetal force and linear orbital speed when it is moved to a new orbit 2h from the surface of the planet? Satellite of mass. We've been doing satellites this entire time. Satellite of mass m. Um. um, what is the new centripetal force and linear orbital speed? So basically, you're just changing h. Oh yeah, there we go. We've got one viewer. What is the new centripetal force and linear speed when it is moved to a new orbit at 2h? Oh, that's sad. What is the new centripetal force and linear orbital speed when it is moved to a new orbit 2h from the surface of the planet? What is it actually? Um, let's see what we can do. What can we do? We can look at the equations. So the height is doubled, right? So r is doubled, and we want the centripetal force. If r is doubled, then the force is divided by 2 normally, isn't it? Because it's not acceleration, it's... No, from the surface. Is in an orbit height from a surface of planet M, centripetal force acting on F. On satellite is F. So we're just adding an H. So yeah, between F and F over 4 should be the answer because we don't know. Linear speed should be, I remember getting this wrong, but if you increase F equals, right, F equals ma, so if you increase, that has nothing to do with it. If you increase R for a constant, what's constant though? M. M is constant. So if you increase R, you're gonna have a smaller g. If you have a smaller g, you have a smaller a. If you have a smaller a, if you have a smaller a, but then r is already in the equation, you're gonna have a bigger, smaller a squared. So there's still one r. It's gonna be smaller. Let's say b. Ooh. Linear speed v also decreases as shown in the equation v equals gm divided by r. Okay, and that's what we had. Oof, 3 more questions to go and we're done. And you'll be done. 2-point charges are separated by a distance r as shown. The negative charge acceleration is 3 times that of the positive charge. What is the ratio of gravitational force to electrostatic force between the 2-point charges? So, first of all, F1 equals K Q1, which is 3e, minus 3e, so minus K 30e, minus 30 Ke squared, if that makes sense. Divided, of course, divided by r squared, which is, in this case, there's no third mass, so we can just use r squared for both. And the other, g, let's just write it down, it's gmm, M1. 2 point. Oh, they're 2 point charges. So they have no mass if they're point charges. So how can there be any gravitational attraction? What do they mean, the acceleration of the negative charge? Why does it have an acceleration? Do you mean it's g? But also they're point charges, so I don't know what you're on about. Let's just see if they're like, oh no, you have to choose one of them. Oops, I didn't see anything. GM1. There is no M1. There just isn't an M1. So I'm gonna have to report this. I don't understand. How can I report this? This? I don't know what that does. I guess I can't. Whatever. Gravitational force divided by electrostatic force. I don't see a way to resolve the problem that we have because it just is. But if we assume the 3, it should be, yeah, it would be this. It would be this. Oh, I guess you assumed it's the same mass. That's a really bad question. An object is swung at the end of a rigid rod in a vertical circle at a constant speed v. The radius of the cylinders r. This is illustrated in the diagram below. The object is swung at the end of a rigid rod. Radius of the circle is r. This is illustrated in the diagram below. Okay, the tension in the rod when the object is at its lowest point in the circle is 50% greater than the tension in the rod when the object is at its highest point. Which of the following expression is equivalent to the acceleration of free fall on Earth? G. Constant speed. Radius of the circle is r. And the circle is. Wait, am I? Yeah, I'm still in frame. Wow, it's a cool setup. The tension in the rod when the object is at its lowest point in the circle is 50% greater. Okay. When the object is at its highest point, which is the following, is equivalent to the acceleration of free fall on Earth, g. So on the top you have mg plus t. Mg tension goes there and g goes there, right? So mg plus t is equal to mg minus is it equal to, no, it's equal to minus t minus mg. But t equals mg doesn't make any sense. T divided by m. If t is this, so it's v squared or m. But that's probably not it. get weight plus the weight. In both scenarios, the object is moving in therefore net force is the centripetal force. Ma equals mv squared. Object is moving, therefore the net force is centripetal force, where m is the mass of the object. Acceleration is always towards the center of the circle. So at highest point, acceleration points downwards, and the highest point acceleration points upward. The tension in the rod when the object is at its highest point, Bt. Yeah, T plus mg. Oh, I forgot to bring 1.5 T. Oh yeah, I forgot to do that. Oh no. Oh no. Wait, what is this? Do I still have internet, right? Whew. Now solving these to eliminate T. Okay, they eliminate T. So basically just solving. Two more. The ball. What is going on? Ball of mass 0. Blah blah is attached to a string of length 0.2 is moving in a vertical circular path with tangential speed. The instance shown in the diagram. Given that sine 6t equals this, there's a tension in the string at the shown point. A ball of mass is attached to a string of length. Okay, at the instance. So we can say, do you know R? Okay, 0.2. So 0.2 I mean v squared. So basically 3 divided by 0.2, so that's 15. Is the centripetal thing? What do we want? The tension. We have the weight. If the weight is here, so I need to resolve the weight. I think that's sine. So that's 3 root 3 over 2. No, sine is, yeah, root 3 over 2 times mg times 0.4 times 4, basically. So 2 root 3. So I would have said the tension so the tension is going to be the whole thing, yeah, minus this, isn't it? Which was 15, so 15 minus 2.3. Did something go wrong again? Guess that's D. The centripetal force acting on the ball is the vector sum of the tension of the string. Yeah, minus mg. Oh, it was cos as well. Centripetal force equals this. So tension equals this plus. Yeah, I thought that's what I Oh, the force, I used the acceleration instead. What is going on? Last question. Okay, let me just do a guess before. My guess is gonna be C. But first, let's do it. Two stars of equal mass m are shown in the diagram. Distance d apart a planet is equidistant from two stars with distance d divided by 2 across the midpoint of the line joining the stars are shown. Star star planet. What is the resultant gravitational field at the position of the planet due to the two stars? So d over 2 is at 45-degree angle. Therefore, uh, d over 2 squared plus d over 2 squared equals x squared. Is a useless thing to do. The square root. So the distance equals this. So d squared, basically 2d squared. So d over root 2. D squared over 4. D squared over 4. That's d squared over 2 square root. So that's the distance. Now I guess you could also do this, the, this, you could also do this and resolve it there. Okay, there, let's just do the resultant. GM, so GM divided by R squared. I think it is C. The distance from each star to the planet, is, where'd you get that from, bro? Let's see this video. The distance from each star to the planet is d over 2 root 2. Oh, yeah, okay. Oh, yeah, okay. The gravitational field strength of one star at the location of a planet is given by gm divided by r squared. Yeah. Oh, true. That was close. But why do you need to resolve? Oh yeah, you get this. You get this, you need to resolve times by 2. Well, that marks the end, doesn't it? So even though we skipped a few, shh, I guess that's the speed run. How much time? Oh, longer than the chemistry one. I mean, there were more questions, it makes sense. And also, I was lost during this entire thing. Yeah, I think that's it. So let's see. How many did we get? 21 views. It's not bad, it's not bad. 21. What else? Revision Village. So we're gonna have to call it off. Sand Monster 95 said he would be back, but apparently not. 100 for that. Sand Monster 95. Now I need to figure out how to end it. Can I end it? Using, let me break my setup. So, yes, goodbye. If you come back, another time, we're gonna do more streams like this. If you're watching this later, um, yeah, we're gonna do more. So don't just watch out and wait for us, for me, for us. Maybe we'll do yeah, some with more people sometimes, and solve more of this revision stuff for the upcoming exams. It's pretty useful sometimes. And yeah, goodbye.